Hello everyone, welcome to the second episode of TS 101 series. So what we are doing is that we are trying to cover the distributed systems concepts under this distributed systems 101 series. We already have the first episode launched, that is we talk basically about replicated state machines, and this is the episode 2. We will be talking about single leader replication. So again, before going to single leader replication, let's quickly look into what replication is. Replication is basically a duplication. I have discussed this earlier as well. When you have multiple copies of data, when you maintain multiple copies of data for the sake of fault tolerance, then that process is called replications. Now, let's understand why will we need replication, right? What are the reasons, or what are the reasons behind using a replicated mechanism, right? So let me clear this up. Okay, let's quickly understand what are the reasons for replication. So one can be if we want our data to be geographically closer. So let's assume that we have a client here. Okay, we have a client and there is a system, right? And the system, so suppose we have one of the server which is located in America region, right? But this client is currently present in India, or basically in the APAC region. So for this client, if he has to get the if he has to send the request all over to the server in America and get the response back, it might take some time. So what we can have is that we can have a replicated copy. So we can have a replicated copy of this server, right? We can have another replica, right? Which can be present in a geographically closer region. So suppose this has been deployed in the APAC region. So now for the client, it would be like efficient to send the request here, right? To send the request to this replica and get the response back. So this can be one of the reasons of using a replicated mechanism, right? Let's come up to the second reason. So I'm going to clear this up. So what is the second reason? So second reason can be a single point of failure, right? Let's write it down. So single point of failure is basically when we have a single dependency and it fails, then our entire system can halt. So suppose we have a system here. So suppose we have a system which currently has one server, right? And there is a client which sends the request to this system and get the response back. Now, since we have a single server, what if this server dies? Or what if there is some mishappening caused to this server? In that case, the entire system will go halt. So to avoid that, what we can do, we can again have a replicated copy, or we can have another replica server which can handle this fault tolerance. So again, so if this server one goes down, then this server can be, or this replica server can be promoted to the, so this replica server can be promoted to the new leader, or basically the replica server can handle the client request and responses. So now if this server one dies, then the client will again send to the request. If the client sends the request to the system, then it will not be directed to server one, it will be directed to the replica, and the response will be sent by the replica machine. So this is another reason why we can uh, use replication. Now let's come up with the third reason. Why are we using replication? I'm gonna again clear this up. Okay. So third good reason can be scalability, right? So there are many systems that can be read heavy. So by saying read heavy, I mean that those systems on which there are a huge number of read requests which are used to be sent by the client. So suppose we have this machine, right? So suppose this is the system and we have a single server here. Let's name it S1 and we have client, right, which used to send request. Now, since this is a read heavy system, we have a lot of clients. So we have C1, C2, C3, dot, maybe a lot of, n can be a very huge number, right? It can be a very huge number, maybe around 10 to the power 5 or something like that. And if all these clients start sending this request to the system and which is handled by this one server, then there is a huge chance that this server can get overloaded. Now, what can happen is that if the server is having a like getting the request in a queue mechanism, then these requests can be queued, and it will take a lot of time for the server to respond to each and every request, and these clients will have to wait. There would be a lot of the response time of the request will be very high. So, in order to avoid that, what we can do is that again we can perform replications. Instead of having a single server, we can have multiple copies of this server, and these servers can also take part in handling the read requests. So now, not only this server, but these servers will also be responsible for accepting the request and then sending the response back to the clients. So these are the three reasons, the three very important reasons on which, by due to which we can have replication, or due to which we have to involve replications, right? Now, now, why we are talking about replication so much? So, okay, we are using replication. We are replicating the data into multiple machine. But what is the issue? It is fine, right? It is fine in the case when the data does not change. So, suppose if the data doesn't change, right? So, suppose we have a couple of replicated servers. Let's name it S1, S2, S3, and S4, which hold a same a bunch of data, and this data is not expected to change. So suppose this is the data which is present in all these replicated servers, right? And this data is not expected to change. Then we are fine. We don't have to get worried about anything because the data is same. So if this is handled by multiple servers, it is fine with it. We don't need to like handle a lot of complexities. But the real complexity happens is when the data is expected to be changed, right? So when the data changes, or basically when we have to handle a write request, then it is very difficult for the replicated machines to handle that, or we have to like come up with some intelligent process to handle the write request. Because when this data has been written or when this data is modified, the copy of the data should be modified in all the servers. So server 1 should modify the data, server 3, server 2, and server 4. The copies of the data, all the copies of the data, the same data item should be modified. Because if the data is not modified, then what will happen is that we will face data inconsistency. Right? There can be a huge chance of data inconsistency. Again, we talked about data inconsistency in our previous lectures. So if you haven't, do give it a watch. Do watch the episode 1, the replicated state machines, and the introductory episode of DS101 series. So data inconsistency is basically when uh, two machines hold the same copy of data, but the data doesn't agree, right? So suppose if I am having a copy of the data, suppose I am having a data X, which is 10 in S1, and in S2, suppose this is 11. Then this is basically a data inconsistency issue because these two servers having the same data item X, but they have different value. The copies are not agreeing with each other, and we don't, we should not, this should not happen basically in the system. We have to come up with some efficient way to handle this, to handle the write request. And this is what we will gonna discuss in this episode, right? So in order to handle the entire thing, we have three ways. So let me just clear this up. Okay, so we have three ways in which we can handle this. So these are called replication algorithms. Okay, so what we call this? replication algorithms. And replication algorithms, basically, we will see three replication algorithms. You might have heard about it. One is single leader replication, another is multi-leader replication, and third one is leaderless. So it is difficult to cover all the three topic in depth in this episode, but yeah, we will cover the first one, that is the single leader replication. So we'll cover the single leader replication in depth. Okay. Okay, great. Let me clear this up. Let's start with the single leader replication scheme. Single leader replication. So, as the name suggests, single leader replication scheme means when we have a single leader in a replicated state machines or in a replicated system. So, if we have a system, right? Suppose we have a system and we have multiple replicated servers, name it S1, S2, S3, and S4. So, suppose this is a replicated machine, right, or a replicated system which has four servers. All are replicated. So what single leader replication says that there should be one leader, or we have to appoint one leader within this system. Okay, so suppose we appoint S1 as a leader of this machine, then this is the single leader, and the rest of them will be called as followers. So the rest of them will be followers. Okay, so all of them will be follower, and the S1 or the server one would be the leader of this machine, right? Now, what is the role of the leader? So suppose we have a client here. Now, in the single leader replication scheme, if S1 is the leader, then if a client is sending write request, or basically all the write requests which are sent from the client is given to the leader. So if there is a write request coming from the client, then this will be handled by the leader. In our case, which is S1, right? And all the read requests can go to any of the follower or the leader. So any machine can take it up, and basically followers take it up. So any of the followers can take up the read requests. If there is any read request, it can go to either of the followers, right? So this is a single leader replication scheme where we have one leader among multiple replicated machines, and the write request from the client is sent to the leader, and the read requests are sent to any of the followers. Okay, I think this makes sense. So yeah, let's move ahead. Now I will talk about two replication process in single leader replication. So basically, replication process, why we are talking about replication process is once once we are sending the write request to the leader, it is the leader responsibility to update its followers about the data item, right? So suppose there is a data item X which was written by the client, and it was updated in leader one, because leader will receive all the write requests. Then it is responsibility of the leader machine to tell all of the followers that, hey, this data item X which I have been holding is updated, or it has been written with the new value. Please update your copy as well, so that we stay consistent, or the entire system stays consistent. So that is the reason why we'll discuss about the replication processes. Okay, clear. I'm going to clear this up. Let's quickly talk about the replication process. So what I told you guys is that um, let's have a system. Again, very similar thing which we drawn earlier. Suppose we have three copies or three replicated machines, and we have a client, right? Now, this is a single leader replication scheme, so we will have one leader. Let's assume that S1 is that leader, right? S1 is the leader. Okay, so it means that all the write requests, if a if a if client says that make x equal to 12, and obviously since it is writing the value, the write value should be, it should be a write request. So if the write request is sent from the client, it should be processed by the leader. Now suppose that all the data item, suppose x, the value of x is initially 10 in these replicated machines. So what will happen is that this write request is sent to the server. Now the leader will update the value, right? The leader will update the value there in their machine, and it will tell the rest of the followers to update their data copies as well. And similarly, these followers should also update their copy of data. So the leader S1 will tell all their respective followers S2 and S3 to update the data item. We'll tell them, okay, I have got a write request to get updated, and please update the value. So, okay, I have updated x to 11. So let's assume that the value of x which was updated was 11. So I'm just going to remove this. Let's make it 11 quickly. Okay, so you got the gist, right? Initially, the value of x was 10. We got a write request to update the value of x from 10 to 11. It went to the leader because since it's a single leader replication scheme, the write request will go to the leader. The leader will update the data item in their machine, and it will tell the other replicas or the other followers to update their data copies as well, and they will update. So S2 updated the data copy of X to 11, and S3 updated the data copy of X to 11. And in this way, this entire machine will stay consistent, right? Okay, I hope this makes sense. This is the reason we are using the replication process. Okay, great. So let's discuss about three replication process, right? Which is synchronous, asynchronous, and semi-synchronous. I'm going to quickly clear this up. Okay, so replication process. So first is the synchronous replication process. So what is a synchronous replication process? So in the synchronous replication process, as the name suggests, the leader will wait for the follower to update their copy of the data and will wait for the acknowledgement from the follower that I have updated this copy of data, and then they will send the final response to the client. So we discussed the previous example. Let's take it up again. And this time, let's take two copies of two machines. One will be the leader and one will be the follower. Okay, I'll draw it like this. So suppose this is a leader S1 and this is a follower S2, and we have a client as well. Suppose this is a client. Okay, we will draw a time series graph. So this is basically in this format, and as we move ahead in the right direction, the time increases. So suppose at this instant of time, right, it fires a write request, right? It fires the write request saying that make the value of x 11, as we did earlier. Right? Make the value of x to be 11. Now the request goes to the leader. What leader does? Leader performs the request of making the updating the value of x to 11, but it also sends the same request to the follower that hey, I have got a request from the client that we should update the value of x from 10 to 11, right? Or whatever value they have, update it to 11, and you should update the copy which you have as well. So what follower got the request from the leader, now follower performs this request. So here it performs the request, and once it is done successfully done, it sends the acknowledgement back to the leader, right? Now, once the leader got the acknowledgement and once the leader is done with its changes as well, right? Whatever changes it has done, it is done with that as well. Now, at that point of time, leader is free to send the response back to the client that, hey, right, response, it can be a success, saying that, hey, you have asked me to update the copy of the data, and I think that this is successfully done. I have like I did this change in my system. So in this way, this synchronous replication process takes place. So this is good. This is good because there is very less chance of failure, because if the follower is not able to update, or basically if there is any chance the follower is not able to update the data copy, it will not send the acknowledgement back to the leader, and the leader will not send the response to the client. So there is very less chance of data inconsistency. So there is one advantage, but there is one disadvantage, that the user has, or the client has to wait a lot of time here. So T is pretty huge. So the response time increases because the leader is not only updating its data item, but it is also waiting for the follower to update their data item as well. And once the follower is updating the data item, once it is done with their update, then it is entirely sending the response back to the client. So this is a big change, right? This is a synchronous replication process. We discussed the advantage and the disadvantage as well. Okay. Now let's move to the asynchronous replication process. I think by the name you must be like, it should have been clear what asynchronous replication is, but again, let's quickly discuss that. Okay, asynchronous replication process. What is this? So, in the asynchronous replication process, as the name suggests, the leader does not wait for the follower to make it change, right? It will not wait for the follower to make it entire change and then it will send the response to the client. It's not the case that happened in the synchronous. It will make its change, it will send the request to the follower to make the change, and then it will send the response. So I'll draw the time series graph. We have a leader, right? Maybe S1. We have a follower machine, S2, and we have a client here, right? Now we have a time series graph. Time increases as we move horizontally from left to right. Now what will happen is that at this particular instant of time, suppose client sent a request to the leader. Same request, update the value of X to 11. Now what the leader will do, that leader will start updating the value, but along with that, it will also send a request to the follower that, hey, update this data item to 11, right? Now the follower will perform this operation, but while the follower is performing the operation, the leader will not wait for the follower. The leader will do its update. Once its update is done, it will gonna send the response, or basically a success, to the client that, hey, I have updated it. It will not wait for the follower to make the change. Once the follower has made the change, whatever the response is, it will send back to the leader, right? It will gonna send the response or the acknowledgement back to the user. So this is the asynchronous replication process. Okay. Now, as the name suggests, there is one advantage and disadvantages in this process as well. The advantage being is that the response time is very less. So the client does not have to wait for the leader to make change to the follower. So basically, since leader is not waiting for the follower to make the change, leader just updates the data item which is present in their machine, and gives the response to the client. So the time is less because the leader is not waiting for the follower to make the change. It is just sending the request to the follower, and then the leader is done. He won't wait for the follower to get the acknowledgement back from it. So the response time is low, but the problem is this is the advantage, but the disadvantage is that there can be a failure. So what if the follower got the response, but it failed here, and since it failed, it sent a failure response to the leader. But in that case, the leader has already sent the response, the success response to the client, and this can cause the data inconsistency because for leader, the data item X will be 11, but for the follower, the data item X will again be the initial value. So let's say the initial value was 9. So for follower, the value of X will be 9, but for the leader, the value will be updated. And this again will cause data inconsistency because these values are not agreeing to each other. Right? So this is one of the major drawback of asynchronous replication. So we discussed two replication process, synchronous and asynchronous. Now let's discuss a third replication process, which is called semi-synchronous configuration or semi-synchronous replication process. So what is this? Let me clear this up. Now let's talk about semi-synchronous. What is semi-synchronous? Semi-synchronous is basically when we have, here we will not only discuss two machines. Let's discuss, we have more than two machines. Let's say we have 3 to 4 machines in our system. Then what will happen is that there will be one leader, and the leader will wait only for one of the follower to get their changes done. It will not wait for all the followers. So in synchronous replication, the leader used to wait for all the followers to do their changes, but in semi-synchronous replication process, the leader will only wait for one of the followers to make the change. And since we have two machines which have the updated copy of data, there is a very less chance of fault tolerance, or there is a very less chance of error which can happen. Okay, makes sense. So again, let's discuss this in a time series graph. So this time we have one leader, say S1. We have two followers. Okay, let's say S2 and S3, and we have a client. Again, there is a time series graph where time is increasing, right? Okay. So suppose at this instant of time, client sent a request to the leader that, hey, update a copy of data item for me. Okay. Again, in the same way, let's client says that, okay, update the value of X to 11. Now, what leader will do is that leader will get the request, gonna perform, but along with that, it will also send the same request to the two followers. So it send this request to the two followers, and these followers, or if there is more followers, it will send this request to other followers as well, and these followers will start performing their operation. But it will wait for only one follower. So suppose it waits for S2. Okay. So leader will wait for S2 follower for make the change. So once S2 makes it change, suppose this is done, it got a success or an OK acknowledgement, and the leader has also done its part. It has also updated the data item of X in their machine. Then the leader will send an OK or a success response back to the client. It will not wait for this follower. So it will make its change and will send back to the leader. But the leader does not have to do anything with it. Leader will not like wait for it. So if rest of the followers also get the request, they will send the response back to the leader, but leader will not wait. Leader will only wait for one of the followers. So in this way, what we are ensuring is that not only we have one leader which has up-to-date data, but along with that, we have one follower as well, which has the updated copy of data. Now we have two machines in which we have the most updated or most trustworthy data, and we can perform in the fault tolerance. We can rely on any of these machines to get the data back or get the original data. So this is a semi-synchronous replication process, which lies in the middle of synchronous and asynchronous replication process. Okay, being done, let's finally discuss the fault tolerance. So, fault tolerance meaning how we can perform fault tolerance in single leader replication scheme. And I'll clear this up again. Let's talk about fault tolerance. So, in fault tolerance, we will talk about two things. One is the leader failure, right? And one is the follower failure. So, since in the single leader replication scheme, we have two followers, or basically we have two types of machines. One is a leader and one is a follower, and both of them can fail. So it is necessary for us to consider both leader failure and a follower failure. Now let's discuss them one by one. Let's discuss leader failure first. Now, if you have gone to my previous episode, there as well we discussed about fault tolerance in the replicated state machines, and we discussed about heartbeat or interrupts. This is a very similar thing which we'll discuss here as well, because that is the way the replicated machines handle fault. Again, suppose we have one leader, say S1, and we have suppose two followers. So we have two follower machines, maybe S2 and S3. And suppose what happened is that leader failed. There was some mishappening, then leader failed. Now in that case, the follower machines in the system should be capable of identifying that okay, my leader has failed and one of us need to step up as a leader in order to handle the request from the client. Okay, so how is that handled? I would discuss that in the previous episode as well, that leader continuously send heartbeats, right? So it continuously sends some heartbeat or interrupt to the followers. Okay? So a leader continuously send the interrupt or basically a heartbeat to the follower. Now since it sends this heartbeat continuously to both the follower has things in mind that okay, leader is sending me I'm getting the interrupt or the heartbeat from the leader. It means that the leader is alive. But if the leader fails, or if the leader fails, then what will happen is that leader won't be able to send interrupts to the follower. So now these interrupts will get stopped, right? And since the interrupts are stopped, and since the followers are not receiving any interrupt or heartbeat from the leader, it means they will get identified that okay, my leader has died. So they will again be identified that okay, my leader has died. Now we should do something. Yeah. So what happens? What they do is that one of the follower will step up as a leader and will now from now on will handle the client request. So suppose we have a client here, right? Make it a C. If the request was sent to the leader, now it will not be sent to the leader anymore, because the system knows that the leader has failed, and it will appoint one of the follower as the new leader, right? So suppose this follower is appointed as a new leader. Now this follower will be responsible for getting all the requests from the client and handling all the requests from the client. So this follower, so all the client requests from now on, any write will be sent to this new leader. And how the follower got identified using the heartbeat. So when the leader died, it stopped sending the heartbeat to the followers, and the followers got notified that okay, my leader has died because I'm not receiving any interrupt or heartbeat from the leader. So one of us have to step up as a leader. One of them stepped up as a leader, and the request from the client, or the right request from the client, start getting redirected to the new leader. Okay, this is the way in which the leader failure is handled. Now let's quickly talk about follower failure. So this is also like not a not a big deal, because leader failure is a big deal. If a leader has failed, then this interrupt and heartbeat thing mechanism needs to be in point in order to people to have a new leader, right? But if a follower has failed, then it's not a big deal. So follower failure is pretty simple. I'll just write a follower failure. So follower failure is very simple. Suppose one of these follower dies. What will happen is that, since followers are only responsible for handling the read request, they don't have to perform a write request. So it is okay. If this follower has died, it is okay to let it go down. Since we have the leader running, we have the rest of the follower running, the rest of them can handle the read request, right? Now the thing happen is that if this follower has gone down for some point of time, and it comes back at a later point of time, it has to understand what updates have been done or what writes have been done in the meanwhile he was gone, right? So suppose this follower was down at an instant t1, and later at an instant t2, it again went up, or it again joined the system. Some failure happened, some crash, uh, due to which this follower got crashed, and after some point of time it went back into the system. Now what should happen is that the follower should be able to understand, or should be able to identify what are the write requests or what are the updates which has happened in the meantime it was gone. How does a follower does that? Using the logs. So whatever changes or whatever write request or whatever request which has been sent to the system, every follower logs it. So follower maintain a log. So it logs each and every request. Now, suppose at particular instant of time t1, the follower went down, which means that its log also went down. Now from t1 onwards, there will be no log present here. So suppose let me clear this up. So basically, from starting t1, there will be no logs. From t1 to t2, there will be no logs in this machine, in this follower, right? Now since follower went back in t2, it can ask for other followers for the updated log. So it can ask for the another follower which was like right, which was there all the time. Hey, I went down on a t1 instead of time, and now I am up at t2 instant. Please give me all the logs or all the write requests or all the updates which happened between t1 and t2 instant of time. And the follower can send this these stream of requests into the log, and it can update its log, right? It can basically this follower can update its log, and it can update its log to t2 instant of time, and in this way it can again join back the system. So follower failures is handled using the log mechanism. If you found this insightful, do like this video, share it with others, and do subscribe to the channel. It will mean a lot. We'll meet in the next episode.